This module reviews scan strategies used for collecting meteorological radar data. A scan strategy is a pre-programmed set of azimuth and elevation angles at which the antenna will point, as well as specification of the PRF and antenna rotation speed, which controls the sampling rate given some PRF. The type of scan strategy used determines the spatial and temporal resolution of the data collected. Two basic types of scan strategies are used for weather radar. The most commonly used one is called the Planned Position Indicator, or PPI. In this type of scan pattern, a preset list of elevation angles is used, and the antenna sweeps through all azimuth angles at each tilt. When the antenna has made a complete sweep at one tilt, it moves up to the next elevation angle and executes another complete sweep. After the last pre-programmed elevation angle, the antenna moves back down to the lowest tilt and repeats the entire process again. A rotation at each tilt is called a sweep, and all sweeps combined are considered one complete volume. PPI scans allow a radar to sample the environment across a large area out to its maximum unambiguous range over a 360-degree circle, but the vertical resolution is usually small as some gaps can remain between individual tilts, especially at large ranges. The Range Height Indicator, or RHI, rotates through a preset list of azimuthal angles and a range of elevation angles. It makes a vertical scan across all elevation angles at a single azimuth, then moves to the next azimuth and scans either back up or down the range of elevation angles. RHI scans provide high vertical resolution of convection, but would take too long to execute to scan an entire 360-degree sector in a desirable amount of time. Because a radar antenna can only point in a single direction at any given moment, a full cycle of a scan strategy often takes 5 to 15 minutes to complete, depending on the requirements of the radar operator. We'll look at some specific types of scan strategy used for cloud radar in a later module, which will include several examples of RHI scans. And at the end of these radar modules, we'll take a quick look at phased array, which overcomes the need of having a moving antenna. The current image is that of radar reflectivity factor from a research radar that used a 15-minute scan strategy and combined PPIs at several elevation angles, seen at the right side of the figure, and RHIs in sectors to the northeast and southwest of the radar, where you can see hash marks on the constant range rings, like right here, for example, and some of these behind the colors up here as well. The elevation angles on the right are shown right here. In this example, intense convection is seen to the northeast of the radar, with some scattered convection located elsewhere. Next, we'll look at a vertical cross-section through the convection along the yellow line shown at the 12-degree azimuthal angle. The two figures show side-by-side cross-sections of the same convection through that yellow line. On the left is a synthetic cross-section made using PPI data that is interpolated to fill in gaps between rays. Note also that this data is collected over several minutes, so it does not represent an instantaneous cross-section of the hydrometeors. On the right is the same cloud, but sampled using an RHI. A couple of things stand out when comparing the two panels. Although the displays look qualitatively similar at first glance, the RHI clearly has better vertical resolution. For example, the radar bright band is seen in a stratiform precipitation area enclosed by the white circle on the right. This bright band consists of a high reflectivity region that occurs near the 0-degree sea level and is caused by melting ice as it precipitates. The same feature is seen in the panel at left, but it is not as well resolved. Additionally, the RHI on the right has a higher maximum elevation angle than the collection of sweeps used to create the image at left. Therefore, the RHI can efficiently see high up into the cloud, fairly close to the radar. You can see the distance in kilometers on the x-axis here, compared to the same thing over here. Very high scan angles are seldom used with PPI scans because their primary purpose is to see the horizontal distribution of echo. Most operational radars use PPIs as their primary scan strategy. The National Weather Service WSR-88D radars call their strategies volume coverage patterns, or VCPs. The VCPs are simply pre-programmed elevation angles and corresponding PRFs. The next couple of slides will take you through a few VCPs used. The one shown here is known as the clear air mode. It is used for long-range surveillance in quiet conditions near the radar. Because the goal is to maximize the unambiguous range, the PRF is set to something low as 314 Hz. However, the long pulse period means that the antenna must move more slowly than normal to capture an acceptable sampling rate. The slow antenna rotation also increases the sensitivity by decreasing the background noise. Various combinations of elevations and PRFs may be used depending on the requirements. This type of VCP generally features a small number of elevation angles, however. VCP 35 is shown in this image and is a little faster than other clear air scan strategies. Various types of other scan strategies are employed when precipitation echo is detected near a radar. In severe weather, the VCP is designed to repeat a cycle as quickly as possible. This is because events like tornadoes can develop rapidly. In fact, there are cases of tornadoes occurring between complete scan cycles and going undetected by radar. The VCPs mainly differ in the PRFs used and the number of elevation angles. A high PRF allows for resolution of large radial velocities, but a lower PRF may be used if severe weather is more distant. These scans are designed to repeat in less than 5 minutes. The middle scan strategy is similar, but includes an extra elevation angle at upper levels to provide better vertical resolution. It is the general precipitation VCP and completes a cycle every 6 minutes or so. The bottom VCP is a special case used when tropical cyclones are near the radar. It uses a smaller number of elevation angles, but repeats some of them, using different PRFs at these low tilts. Again, the higher PRF is used to identify the large Doppler velocities that may be present in a tropical cyclone, at the expense of not being able to see as far unambiguously. As we discussed in a previous module, one limitation of PPIs is that the highest elevation angle, 11 degrees in this example, used generally does not sample an area directly above the radar. This area is sometimes colloquially known as the cone of silence. If looking at a plan view of radar data in XY coordinates, or azimuth and range coordinates, an empty region at the center of the display illustrates where no elevation angle is high enough to sample. This example shows how also the no echo region expands laterally from the radar as we move up in altitude. When designing scan strategies, we consider the beam width of the transmitted signal as well as the spreading of the beam. Recall that the beam width is defined as the angle that contains the half power points of the antenna gain function at the center of the main lobe. However, because the beam spreads as it moves outward, the spatial resolution of data far from the radar is less than it is close to the radar. Therefore, a small echo may be captured by even as many as multiple azimuth angles if it's located really close to the radar, but might fit completely within a single beam if located far from the radar. Azimuthal angles in a scan strategy are often separated by about 1 degree, which is a typical beam width used for operational and many research radars. We also must consider refraction of the radar beam as it moves through space. The atmosphere, and particularly water vapor, causes the beam to bend downward toward the surface. And that's called refraction. However, additionally, the surface of the ground bends down and away from a horizontal beam path. This must all be considered when determining the height of an echo sampled at each range gate. Note that super refraction can cause the beam to bend downward even more than normal, and in extreme cases the beam can actually bounce off the surface, returning power associated with stationary echo on the ground. Finally, consider the following situation and try to design your own scan strategy for the given requirements shown here. There's no one single answer, but the requirements are ones that are often considered by radar operators. And the answers you get to the questions at the bottom about the PRF, elevation angles, and the antenna rotation rate are things that can be controlled by radar operators, and the values that you get should be close to ones that are used for actual radar remote sensing.